how to convert from decimals to proper fraction. So a proper fraction is when the denominator and the numerator are both integers. So if we're going to start with an easy example here, open 5 into a proper fraction. We're not finished by just doing this because this is not an integer, but this is. So to do this, turn this into an integer, we can multiply this by 10. And we can do this even without changing the value if we multiply the denominator by 10 as well. So first little simple example here gives us this times 10. Same number as this one. But now we have a proper fraction with 5 over 10. And this can be simplified into 1 over 2. And this is the simple example of converting from decimal to a proper fraction. But how do you do when you have something more complicated, like this over here? Here I already printed out the answer, but if it's an infinite sequence of decimals, repeating, how do you figure out what the proper fraction is for that one? It's a bit more tricky than this, but it's still very doable. And yes, I believe you can do it as well. We'll start like this. We'll name a little variable x to the infinite sequence here. Whoop. 0.27, 27, 27 into infinity. Yes. And we're going to start by doing a little trick here. Let me just do the trick and then explain why it's important, because it's more obvious in that order. So I'm going to multiply this by 100. I'm picking 100 because the repetition restarts after the hundredths parts. So this turns into 27. That makes the whole repeating sequence, which is 27 here, to be out on the left side of the decimal sign. So it's just that little fact. So the whole repeating sequence is now on the left side of the decimal point. But we still got this infinite sequence of 27s going on forever. So we haven't handled them yet. We just moved everything a bit to the left. Having done this, we can now follow through with our trick. So 100x minus x equals 27.27. No, that's not a 7. 27, 27, 27 into infinity minus x, which is this over here, 0.27, 27, 27 into infinity, giving us 99x. This part of the side of the equation is pretty simple. But what happens here? And this is what's clever. Doing this actually eliminates the infinite part of the expansion here, of the decimal expansion. Because we got 27, obviously, yes. Whoop. But this part here is equal to x. And this here is equal to x. So when we subtract here, these cancel each other out. So 99x is actually 27. This is very good, because now if we want to continue getting our proper fraction of this here, we just have to solve for x. And then we get 27 over 99. That's actually it. That's a proper fraction. But if you look at where I stated the problem, I said this was the finished answer. So how do we get to there? Well, from here, it's only a matter of simplification. And I'm going to show you a little neat trick on how to do that in a good way. So I like to use prime number factorization to make this a very simple step. And then you do it like this. So it's called prime factorization. I'm not going to go through it exactly in this video, but you can find something else on the internet that tells you how to do it. But we find the prime numbers for this number here. So 3 is a prime number, giving us 9. So 3 times 9 is 27. But this can still be factored into more prime numbers, 3 and 3. So these are all the prime factors for 27. Now we're going to do the same for 99 99. So we can bring out the 3. Then we get 33. And then we can bring out the 3. And we get 11. So I prime factored 27 and the 99. And then we can rewrite this fraction like this into 3 times 3 times 3 over 3 times 3 times 11. This is obviously the same because 3 times 3 times 3 is 27 and 3 times 3 times 11 is 99. And when we have done it in this form, it's easy to just cancel out the common factors. Then we get 3 over 11. How neat, isn't it? Now we have done this. We have converted this infinite sequence of repeating patterns in the decimal into a fraction. And we've done it for a simple fraction, and we've done it for this one. But there's one step more that can make this a bit more complicated. And we're going to do one last example, but you already got the basics of it, so this is enough. But now for the, what do you call, advanced course. All right. So what if our problem doesn't start with the repetitive sequence? So if we want to write the proper fraction for this 5.1999 infinite sequence. Okay. It's not as obvious what to do here because the infinite sequence isn't the whole number. It doesn't start until right here. So how to do it here? Well, basically the same technique. We're gonna name x into our number, into 5.1999 infinite sequence. And then we're gonna do the multiplication of x until we got the start of the sequence to the left-hand side of the decimal point. And again, this actually is by 100. So the sequence starts at the 100th point. So we're going to do 100 once more. 100x equals 519. And then the 999. So we get the whole infinite sequence of decimal expansion on the right side of the decimal point. And then we can actually do the same as we did last time. We can remove the infinite by removing one x from here. So we're gonna just take 100x minus x. Then we get 519.999 minus 5.1, and then the infinite series of 9s. And this is because this part here will cancel out this infinite part here. Once more. So what do you get when you do that? Well, let's do a little the little standing calculation here. Let's do it like this. So 51999. Yes. Ooh. Yeah. Minus 519. Ooh. So the decimal point is here. And this turns out to be 9 minus 9 is 0. 9 minus 8. 4, 1, 5. So 5140 with the decimal point there. Perfect. So the 9x is just below here. I'm going to multiply everything with 10 once more just to make things simple. So our 99 turns into 990x. And then we get the number here. 5148. And then we can solve for x. And we get x equals 5,148 over 990. We can actually use the same technique when we want to simplify this, as I did last time. You just need to think a little bit more about the prime factorization tree. So if we do this here, we're going to have 5,148. And then we're going to start prime factoring. It's an even number, so we can break out the 2 here. That's one prime factor. Then we can divide this by 2. That is usually a pretty simple operation to do. You get 2,574. I know that by practice. And this is also even, so we can break out another 2. And then we go from there. We can half this again, and then we get 1,287. And this thing here is 1 plus 2 is 3, plus 7 is 10, so 18. That means the sum of the numbers here are 18, and that's divisible by 3. So this is divisible by 3. Very good. And to calculate that, I'm going to use the lying share method. I don't know if you call that. Maybe you call it stair division or something. I just like it. 1, 2, 8, 7 divided by 3. So 3 fits in 12 4 times. And I'm going to write. And it fits in this 2 times. And we get 27 down there. And then it fits in there 9 times. So this turns into 3 and... What did I do there? I just write the 3 just below. That's weird. I should have made a little shoop. 3 and 429. And then 429. I'm going to make a guess that is divisible by 11. Because it seems like it. Yes, it's divisible by 11. Then I get 39. And 39 is obviously divisible by 3. Then you get 13. All right, that was quite the huge prime factorization tree. And we actually have to do the same for 990, but that's quite simple. Let's do it. Let's do it here. I'm going to start it here, just below this tree. So 990. And we can bring out a 2. And then we can bring out... Actually, let's not start with that factor. Let's do this. I usually start with the prime numbers, but we can do it 10, and then we get 99. And then from this one we get 2 and 5. Here we get 3, 33, 3, and 11. All right. Now we can look at the prime factorization trees and cancel out the common factors. So we got the 11 here. Cancel out this 11. We get the 3 here, canceling out 3 here. I think we had another 3. Yes, that 3 there. Cancel out this 3. And then we have a 2. We have a 2 here. Cancels out this 2. And then only a 5 left. So we have... This must mean that x equals... No. I'm going to move it down a little bit. Looks better. X equals 2 times 13. over 5, which is 26 over 5. And that's it. You watch me do it all by hand. No calculators involved. And I actually think it's a good practice to learn how to do this without any calculators, because it's good for your arithmetic skills. I don't expect you to have this by flow when you're watching this video, but it's a good practice. And you saw me how I did it using no calculators. This prime factorization method is very useful. You see, I skipped a lot of calculations. I broke it down into smaller parts. I used this trap division method, stairs division, something like that. I don't know the English phrase. And it also makes it simpler to do calculations. I'm going to do a video on this. I'm going to do a special video on prime factorizations. And well, we showed a lot of useful stuff in this one video. Anyways, the important step on how to do the fraction conversion when you have an infinite sequence is that you want to remove the infinite sequence by first multiplying it to the left of the side of the decimal sign. And then by this subtraction here, you remove what's infinite. So you get something that you can handle and do the writing round. I just use the prime factorizations to help me simplify the fraction. But that's about it. Thank you so much for watching. I hope it was helpful. If you have any questions, ask them in the comments and I'll gladly help. Blah, blah, blah. And I need to go and drink some water and make myself some lunch. Thank you so much for watching. You might see more of me. Goodbye.